So, in the last lecture we saw second proof of finiteness of class group, where we use geometry of numbers. So, we found precise conditions on a set so that it has non-trivial intersection with a lattice. We used that result to prove finiteness of class group, but we did not have to make a choice of this set S that we had. Today we are going to make a good choice of S, so that we get a bound as good a bound as possible. I am not going to justify why this is the best possible choice or anything, but I am just going to tell you that it is the best possible choice. So, recall that we had a certain quantities. So, S is a bounded, closed, convex subset of R n, symmetric about the origin, and we had two quantities. M was the maximum of a product like this. So, M was max over all x in S, x 1 up to x r 1, and then x r 1 plus 1 squared plus x r 1 plus r 2 plus 1 squared, etc., up to x r 1 plus r 2 squared plus x r 1 plus 2 r 2 squared. So, it was maximum of this product as x varied over all of S, and V was volume of S. Okay. And the quantity that we got, the bound that we get, so the relevant quantity is 2 to the power r 1 plus r 2 times m by V. So, this is the quantity that we are interested in. So, today I am going to tell you a good choice of S. So, the following set S is a good choice. Okay. And as I said, I am not going to justify why this is a good choice, but you will see in practice that this gives us good bounds also for practical reasons. So, you take all x 1 up to x n in R n such that the following holds: summation I going from 1 to R 1 mod of x I plus summation j going from let me write it like this, R 1 to R 2 x R 1 plus j squared plus x R 1 plus R 2 plus j squared, and then square root of that. Okay. So, this is less than or equal to 1. So, that is the set that I am going to take for S, and we have to prove a bunch of things about this. So, what do we need to prove? S is bounded, closed, convex, and symmetric about origin. So, bounded is clear. Because it is given in terms of you take some modulus as well as distance, like Euclidean distance, and it is less than or equal to 1. So, you can't have any point where any coordinate is bigger than 1, for example, right. So, it is bounded in a very strong sense. So, this is fine. closed is also fine, right, because it is given by a closed condition, right, it is less than equal to, not less than. So, closed is fine, and convex is perhaps slightly trickier. So, for convex you use, so you can take this as an exercise if you like, an easy exercise, both proving the this inequality as well as using it to show that something is convex. So, t times square root of x1 plus y1 plus 1 minus t times square, sorry, this should be square, x1 square plus x2 squared plus y2 squared is bigger than or equal to square root of t times x1 plus 1 minus t times x2 squared plus t times y1 plus 1 minus t times y2 squared. Okay. So, proving this inequality as well as using it to prove convexity of S, these two are exercises. Okay. And lastly, symmetric around origin is also clear because the condition is in terms of either modulus or square. So, this is also fine. Okay. So, we have our set S has all the properties that we need of it, and so we need to compute M. So, want to compute M as well as V. So, want M, which, let me remind you, this is max overall X in S, right, and because it is a closed and bounded set, I am writing max, not supremum. Maximum is attained, right, just a technical point. Sorry, this should be, okay, that is not how I wrote it. So, let me write it in the way that I wrote it. So, this is mod x1 up to xr1 times xr1 plus 1 squared xr 1 plus r2 plus 1 squared and half square root of that x r1 plus r2 squared x r1 plus r2, sorry, 2 times r2 plus 2 times r2 squared and square root of that. So, this product, it is a max over this product. Okay. And V is volume of S. So, we want to compute these two quantities. Okay. Now, or at least get an upper bound on this. So, M is less than or equal to, this is by the arithmetic mean geometric mean inequality. So, AM GM inequality, right. So, nth root, well, not nth, plus r1 plus r2th root of this kind of thing is, sorry, I think I made a mistake here. Yeah, there is no half here, there is no half here, sorry. So, that is an error. I hope I wrote the right thing on the slides above. Yeah, there is no square root there, right. Okay. So, this is fine, right. Okay. All right. So, what I do is okay. So, the reason I got confused is because of this. So, let me write it in a different way. Okay. So, this is max X in S, and then I am going to write it as x1, well, mod of x1 and so on, mod of xr1, okay, and then I am going to write this thing as square root of xr1 plus 1 square plus x r1 plus r2 plus 1 squared, and I am going to write the same quantity twice. So, x r1 plus 1 squared plus x r1 plus r2 plus 1 squared, and so on up to x r1 plus r2 squared plus x n squared, and then the same thing again, x r1 plus r2 squared plus x n squared. Okay, so it is a max over all these things. So, now you see there are n terms here, and I think and so if I take nth root of that, that will give me geometric mean of these n numbers, and so I can use the geometric mean arithmetic mean inequality. So, AM GM inequality will tell me that this quantity, this product is less than or equal to its arithmetic mean to the power n, right, because I am not taking nth root here. So, this is less than summation I going from 1 to n mod of xi plus the way I am going to write this is summation j going from 1 to r2, right, j going from 1 to r2, and then these quantities, right. So, 2 times square root of x r1 plus j squared plus x r1 plus r2 plus j squared, and divided by n, and then I am going to take whole to the power n, and so I made another mistake here. I should, my symmetric set S should be 2 times this, right, sorry. So, my S should be this 2 times this, right. So, that yeah, okay. So, now I have what I want, and then this quantity by the definition of set S, this quantity is less than or equal to 1, right. So, I get this is less than or equal to n to the power minus n. Okay. So, that is my inequality for m, and remember I just want an upper bound on n, and in fact this upper bound is attained because we know when arithmetic mean, geometric mean, the inequality becomes equality, right. So, we can easily find points where this is attained. So, this is a sharp bound. Now, the more tricky computation is of V, which is volume of S, and I am just going to give you a few steps and ask you to figure out the details, because this is just some sort of multivariate integration. So, the claim is V is 2 to the power r1 2 pi to the power r2 times this quantity d r1 r2 of 1, okay, where what is this d r1 r2? So, d l comma m of t, this is a function of, if you like, 3 variables, where I take integral over r l m t y1 up to ym, and then d x1 dxl dy1 up to dym. Okay. So, the function is just the constant function 1 in variables xi's, and then in variable yi's we take this particular thing. I still have to tell you what the region of integration is. So, R L M is of t is equal to, So, all points in so x1 up to x L, y1 up to y m such that x i's are bigger than or equal to 0, y j's are bigger than or equal to 0 for all 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to. So, I is between 1 and L, j is between 1 and m, and unsurprisingly you have this plus 2 times y1 and so on up to ym. This is less than or equal to t. Okay. So, that is my region of integration. Okay. All right. So, how do we prove the claim? So, there are two things we need to do. We need to prove the claim and we need to compute this. So two things to do. Prove the claim, that is one thing, and then compute d r1 r2 of 1. Okay. All right. And the reason why we do all this elaborate thing with L, M and T is because one does this by integration by parts, and so one changes the variable L, M, T etc. to get what you want. Okay. All right. So, how do we do this? Well, so let me tell you, let me give you a brief sketch of how you do the claim. So to prove the steps to prove the claim. So, what is V? V is volume of S, and how do you define volume of S? This is integral over, so let me be consistent with my notation, right. Yeah. Okay. So what you do is you you just integrate all these. Yeah. So my notation is now not consistent because I am using xi's there as well, but let me just say dx1 up to dxn. Okay. So these are the original coordinates, and s varies over this. So what I am going to do is I am going to change variables x r1 x r1 plus r2 plus 1. So these into polar coordinates, and so on. So again x r1 plus 1, x r1 plus r2 plus 2 into polar coordinates and so on. Okay. So what I get after that is V is integral over, so this will be y 1, so the one here times something, so times e to the power I theta 1 or something, you know. So y 2 e to the power I theta 2 etc. So just by the way things are arranged, this will be y 1 up to y r 2 and then dx 1, the first r1 things do not change, and then with the polar coordinates you just get y1 up to dy r2. Okay. And then because of the change of coordinates you will get your constants in there, right. So, so let me just directly write not r1 r2 1, and then because the region of integration changes in a certain way, right, your x1 up to x r1 are allowed to go from -1 to 1, but the region of integration, this r, is only from 0 to 1. So, you get a 2 out of each of those. So, you get 2 to the r1, and similarly with the polar coordinates, you are allowed to vary your angle between 0 and 2 pi, and your y goes from your xi's go from -1 to 1, but your y only goes from 0 to 1. So, you get 2 pi to the power r2. So, that is where you get these constants from, and so this is roughly the steps to prove the claim. And now next would be how to actually compute. So, steps to compute d r1 r2 of 1. These computations are best done by yourself. So, that is why I am just going to give you steps. It is not going to be any illuminating if I do them here for you. Okay. All right. So, for that the sort of by integration by parts you get the following things. So, if I take d, l, m and t, then this is same as integral going from 0 to t d l minus 1 m t minus x dx. Okay. So, all I am doing is changing one of the variables between the first L variables, I am integrating over that, right. So, so this is this is some elementary calculus exercise, and then there are two claims in here. First it is equal to this, and then secondly so first tells you what happens when you vary the first variable for one of those L variables, or you can do it with the y variables as well, and you get integral from 0 to t by 2 dl m minus 1 t minus 2y y dy. Okay. So, this is how you go from a large L and M to a smaller L and M, and then we have various direct calculations for smaller values of L and M. So, that is first claim or first step, and what happens if L is 1 and M is 0, this is simply integral from 0 to t dx. So, this is t. What happens if L is 0 and M is 1, this is integral from 0 to t by 2 y dy. So, this is half t squared by 4, right, and therefore, what you get in the end is the following, and so hence you deduce the following dlm of t. You use step 1 repeatedly until you reach either 2 or 3, and then you get the following, that this is 4 to the minus m t to the l plus 2m divided by l plus 2m factorial. Okay. So, this is by using induction on L and M. So, again these claims are all exercises if you like. Again there is no point in me going over this in detail here. Okay. So, the upshot of all this is the following. Two to the r1 plus r2 let me not get this wrong. So, R1 plus R2 m by V, this quantity I will denote by CR1 R2. This thing now is well, it is strictly speaking less than or equal to. So, this thing is less than, because we just have an, yeah, I just proved an inequality about m, but as I said that that value is attained. So, that inequality is actually an equality for m. So, I am just going to write that here, and when you substitute all the quantities in, you get 4 by pi to the R2 n factorial by n to the power n. Okay. So, let me write that again here, R1 R2, because this is an important quantity that you should remember. It will help you compute ideal class groups. So, this is called Minkowski constant. Minkowski constant. Okay. So, the upshot of the last this lecture as well as the last lecture is the following. So, let me write it down for you here. Let f be a number field with R1 real places and R2 complex places, then any ideal class in the ideal class group of F contains an integral ideal with norm less than or equal to CR1 R2, which now we know is 4 by pi to the R2 n factorial by n to the power n. Okay. So, that is the upshot of this. Now, let us look at an example, the same example that we had last time, where I showed that the first proof of finiteness of class group gives a really ridiculously large bound for norm of these ideals, integral ideals. So, let us look at the same example again, q square root of minus 5. I actually yeah, that is the Minkowski bound, but what I wrote here is not quite right, because discriminant should come into picture somehow. So, this should be mod of df to the half, yeah, sorry. Okay. The Minkowski constant times the discriminant. So, of course, it depends on the field through its discriminant, and also R1 and R2, but more importantly through discriminant. Okay. So, what is the discriminant of this field? This is minus 20, right. The integral basis is, we have computed before, is 1 and square root of minus 5, and so discriminant is minus 20. R1 for this is 0, R2 for this is 1, and so the bound that we get is, so let us look at it again, 4 by pi to the power 1. So, 4 by pi, n is equal to 2. So, 2 factorial by 2 squared times square root of 20. Okay. So, what is this quantity? This is 4 by pi times 2 by 4 times square root of 20, right. And even if we are very coarse in how we compute this, this is 2 by pi. So, maybe I will write less than right. So, instead of pi I will put 3, instead of square root of 20 I will put 5, and so this is equal to 10 by 3, which is certainly less than 4, right. You can get better bounds than what I am doing, but maybe you can get less than 3 also by putting sort of good enough approximations for square root of 20 and pi. But anyway, this bound you see is much better than 145 factorial that we got last time. So, we just have to check what happens to integral ideals of f with norm less than 4. Okay. So, norm 2 or norm 3, norm 1 ideal will of course be the whole ring, right. So, we will do these kind of computations to compute ideal class group in future lectures, okay. But for now we will stop with the results on ideal class group here. In the next class we will move on to units in the number fields, okay. So, from ideal class group we will move on to units, and we will prove a very important result which is called Dirichlet's unit theorem. Thank you.